Hello, and welcome to another URSA example. In this one, I'm going to solve three differential equations using Laplace transforms. And I don't actually know the math behind Laplace transforms, but I can sure code them in URSA. I found these three problems that I'm going to solve by Googling Laplace transform problems. So here they are. I'm going to solve these. These are pretty simple differential equations, and I haven't implemented too much in the way of Laplace transforms, but enough to solve these equations. So let's get started. Let's do equation 1. Equation 1 is this. It is y prime equals 5 minus 2t, y is a function of t, with the initial condition that y of 0 equals 1. So I'm going to put in the initial condition first. And the way that you put in definitions and initial conditions and things is by making an assumption. There are lots of things that assumptions are used for, but one of those things is making definitions. So I'm going to say assume, and definitions are called equalities in URSA right now. Equality, and in square brackets you kind of put the name of the equality, and then a colon, and then the data of the equality, which is that y of 0 equals 1. So when I run this, under assumptions there's now a user tree, and it shows equalities, and basically what I just typed in. Now I would actually like to take definitions and put them in this window so you don't have to drill down into assumptions. Assumptions are used for so many things. I need to break this up a little bit. But anyway, so there's our equality. And I will put this differential equation in now that we've got our initial condition. So set the expression to the derivative of y with respect to t equals 5 minus 2t. Okay, so we can now solve this with a Laplace transform. The first thing that we need to do is take the Laplace transform of both sides of the equation, which we can do with the Cong rule, equality.cong, which Cong stands for congruence, and it applies some function to both sides of an equality. So I'm going to apply Laplace transform of t, s. That is a Laplace transform that transforms a function of t into a function of s. And so that's just been applied to both sides. So now our equation is the Laplace transform of this equals the Laplace transform of that. And these are totally inert. It's just saying it's the Laplace transform of something equals the Laplace transform of something else. So now we need to evaluate these Laplace transforms. And we can do that pretty easily using, there's a rule called Laplace transform that evaluates Laplace transforms. And if you run it, it just evaluates the Laplace transform sort of one step. So right now I have the right-hand side selected of the equality, and if I run this, it's the Laplace transform of 5 minus 2t, and if I run it, it'll just turn into the Laplace transform of 5 plus the Laplace transform of negative 2t. And that's because the Laplace transform of a sum is the sum of the Laplace transforms. So it's just evaluated that one step. But we can do that all at once. I will undo that. There is a rule called top-down. It's recursion.topdown. And you give it the name of a rule, which I will give it Laplace transform, and this will run that rule on every expression top-down throughout the whole selected part of the expression tree. So when I run this, it just takes all of the Laplace transforms all the way down and just rewrites that all the way done. So now we've got that for our right-hand side, which is now a function of s. And on the left-hand side, we're going to take the Laplace transform, but only take it one step. So that becomes this. The Laplace transform of a derivative is this. So now we've got y of 0, which is our initial condition, and I can navigate into that and say substitute, and then give the name of the equality, which is y0, and that substitutes the equality. So now the next thing that we want to do is isolate the Laplace transform of y on the left-hand side. So I'm going to add 1 to both sides of this equation and simplify it, and then divide both sides of the equation by s and simplify it. And now we just need to take the inverse Laplace transform, which we can also do with the Kong rule. And now we're changing the variable s to the variable t. So now we're going to use a rule that's much like Laplace transform, but it's inverse Laplace transform, and this rule evaluates inverse Laplace transforms. Here I've got the left-hand side selected now, and we have the inverse transform of the transform of something, which the inverse of the thing is just... they cancel, basically, so we get y when we evaluate the inverse Laplace transform. And now, on the right-hand side, we've got these funny fractions that actually we should deal with. There's 5 over s times s, and there's 2 over s squared times s. There's a rule that I just added for this situation. It's called combine like terms, and you give it the name of a term that you want to combine powers of, which I will give it s here, and this will basically combine like powers of s. And I actually would like to run this top down on the expression tree. So top down combine like terms of s, and it takes that s times s and turns it into an s squared and so on. So now we can do top down inverse Laplace transform, and that's the answer. And we can simplify this a little bit, run the simplify rule, and run the arithmetic rule. This is kind of granular. Actually, simplify could take sort of arithmetic calculations, but they're different rules right now. Anyway, the arithmetic rule does the arithmetic and takes that. I'll just undo real quick. We had t squared over 2 factorial times 2, and when I run the arithmetic rule, those cancel. And these ended up reordered. The rule wasn't supposed to do that, but anyway, this is correct. So we've got y equals 1 plus 5t minus t squared. So let's do the next equation, next differential equation. Now, we have this initial condition here, and actually I haven't implemented yet getting rid of assumptions. There should be a minus sign or a trash can or something so you could get rid of this assumption, but there isn't. So I'll just refresh the page and make a new assumption for this new equation, or actually 2 assumptions. So I will say assume, and I might rename assumptions to definitions in the future. They are used for a lot of things, but definitions might be a better name for those. So we're going to assume an equality. I will call it y0, and the data of it will be that y of 0 equals 0. That's the second one. And then assume, I'll call the other one dy0 for the derivative of y at 0. And that's going to be that the derivative of y with respect to t evaluated at 0 equals 0. So now we've got these 2 assumptions, both of these. And now I'll set the equation to be this differential equation, that the second derivative of y equals 10. And now we can take the Laplace transform of both sides. Transforming t into s, and then on the right-hand side we can just take the Laplace transform straight away. Easy. And then on the left-hand side, we can take it just one step, not top-down, and that gets rid of kind of one derivative. This quantity right here is one of our initial conditions, so I can say substitute dy0 because that's the name of the condition that it is. And then I can simplify this to get rid of the 0. Then go in here and take the Laplace transform again. And then this is our other initial condition, which we can get rid of. And then I'm also going to use the combine like terms rule again to combine those 2 s's into an s squared, and then divide both sides of this by s squared in order to isolate that Laplace transform. simplify, and then I'll combine like terms on the right. And then take the inverse Laplace transform of both sides. From S to t now. And then run the inverse Laplace transform rule, so this will cancel out the Laplace transform with its inverse. And then top down, run inverse Laplace transform to just take that all the way. And then we can simplify this. There's a times inside of a times, which there's parentheses show up here. But I will just simplify this and then run the arithmetic rule to simplify the arithmetic. And we get 5t squared. So that's the solution to this other differential equation. So now third and final one. This is going to be slightly different. It's a different solution that we get, not just a polynomial. See if you can guess what it is. I will put in the two initial conditions. Equality y is that y0 equals 0. That's right? And then dy0 the derivative of y at 0 equals 1. So these are our initial conditions, and then I'll put in the differential equation. The second derivative of y with respect to t plus y equals 0. And now I'll run congruence Laplace transform to take the transform of both sides. And this right hand, we can just simplify straight away real easy. Just take the Laplace transform, and then 0 over s we can just simplify to 0. On the left-hand side, we're going to do this a little bit more step by step. So instead of doing, say, top-down Laplace transform, which we could do, we'll just run it once and work with what we get. So that took the Laplace transform of a sum into the sum of transforms. And then I'll do that again on this left-hand, sort of more complicated one. And that turns into this, which this is one of our initial conditions. Substitute dy0, so that becomes a 1. And then Laplace transform, I like the Laplace transform, not the inverse Laplace transform. Then this is our other initial condition. So substitute y0, and that becomes a 0. And now I'll just kind of like back out to the top level expression and simplify it. So now we've got this on the left-hand side, and we want to isolate the Laplace transform of y so that we can then just take the inverse. So the first thing that I'll do is add 1 to both sides to get rid of this minus 1. Add 1, and simplify. And then I will combine like powers of s here. Combine like terms on s. And then we have s squared times the Laplace transform of y plus the Laplace transform of y. And we can factor out the Laplace transform using the factor rule. Factor out the Laplace transform from t to s of y. And that just pulls that out. So now we can divide both sides of this equation by s squared plus 1 and simplify this. And then we've got the Laplace transform of y equals 1 over s squared plus 1. I ran flatten before I ran simplify because, well, there's a little bit of an issue with the simplify rule, but the math is correct. Anyway, we just need to take the inverse Laplace transform of both sides now. From s to t. And then on the left-hand side, we can just cancel that. And on the right-hand side, what's the inverse Laplace transform of this? Well, it's in the table. It's sine of t. So y is sine of t. So that's it. We just solved this with Laplace transforms. And I'll just show you very quickly how that rule works. The Laplace transform rule, if we go into rules, under built-in, the Laplace transform rule, if I type this in and tab complete it, it's in calculus.laplacetransform.Laplace transform. So we'll go to calculus, Laplace transform, and this is the definition of the rule. So it says slash rule, and then this is the name of the rule, colon, and then there's a left-hand side and a right-hand side. The left-hand side is what's pattern matched when you run the rule. If you run it on, in fact, I'll just undo and show this is an inverse Laplace transform, but it's the same idea. This is inverse Laplace transform ST applied to something. So this rule, when you run the Laplace transform rule, it looks for Laplace transform something t, something called s, and then something. And these t, s, and f can be anything. They get pattern matched, and these underscore variables get bound to whatever is actually in here. So this is the left-hand side, which is pattern matched. Then after you run the rule, the right-hand side is what's substituted into the expression. So when you run this rule, it takes this and then replaces it with this. And the after the left-hand side and the right-hand side of the rule, you might be wondering, well, what's g? How does it know what that is? Well, there's a rule can also have any number of clauses after the left-hand side and the right-hand side. And this rule has one clause, which is this. The clauses come after this symbol, colon minus sign, which is a left-pointing arrow. And this symbol is from Prolog. I picked this symbol because these clauses are basically horn clauses with a lot more stuff in them. Horn clauses are from Prolog. You can look them up if you really are curious. But anyway, this rule has one clause, and it defines what g is. So that clause is that g is this, Laplace transform that word again, applied to these three things, t, s, and f. This Laplace transform actually refers to an assumption. And this kind of indirection where we have a rule that refers to an assumption, I don't really like this, and I might change this so that instead of having one rule and the assumption we'll look at soon, that there's just rules. But anyway, let's go look at the assumption. So the assumption under built-in, there are a lot of assumptions, by the way. These are used for lots of things. Under Laplace transform, this is what that is defined as. So Laplace transform t, s, and f, this is defined as I, which is the integral of f times this exponent as t goes from 0 to infinity. This is the definition of the Laplace transform. But actually, when that rule is run, these are all tried from the bottom up. And this is really a table of Laplace transforms. So the idea that the Laplace transform of a sum is the sum of Laplace transforms is this second one. It says that if you have the Laplace transform from t to s of any sum, then what you get out is the sum of the Laplace transforms. And this, you don't necessarily need to understand the whole syntax of this. I'm just indicating how this is structured. This is basically a table of Laplace transforms, like you would look up on Wikipedia. And so if some case is not present here, you can add it. You can just say, assume that the Laplace transform of this is this. And then it'll run. So that's about it. Actually, there's one more thing that I can show. Let me back out and create a different equation here. I'll just set Laplace from t to s of y. So you may have noticed that this has an L and then a little t arrow s indicating what variables it's taking the function between. And the LaTeX output here is actually defined with assumptions too. If we go under assumptions built in all the way down to LaTeX output, this is the code for how LaTeX is generated for everything that generates its own LaTeX, and here's the one for Laplace transform. So this is an assumption, and if I take this code, I can change how this is displayed. I can click this plus to make the command window bigger and just paste this in. And if I don't like the T arrow S, I can change this code. So this says that to display Laplace transform TS, man, all these red squigglies from the autocomplete. Anyway, to display Laplace transform TS, it takes the LaTeX string for the T, takes the LaTeX string for S, and then concatenates that stuff together with math skr L underscore T right arrow S. So if I don't like that arrow, I can just remove this and just say that it's just math skr L. I can just really remove a lot of this stuff. And I can change this to an arrow. I'll explain how this syntax works in a later video, but don't need these anymore. Anyway, if I run this, this changes how the LaTeX is displayed, and now it's just L of Y. So this is the LaTeX is configurable. So if you don't like how something is displayed, it can be adjusted. And there could even be settings, like display integrals this way or that way. But anyway, so much for Laplace transforms. See you next time.